In this module, you will refresh your knowledge about plane mirrors and learn about spherical mirrors. We use plane mirrors for personal grooming every day. However, not many of us know how we are able to see a likeness of ourselves in the mirrors. The images that you see on a polished surface can be explained with the phenomenon of reflection of light. We can identify opaque objects immediately on seeing them, as a part of the light incident on them is reflected. When such a reflected light is incident on shiny surfaces, like mirrors, they form images of those objects that have been reflected in them. You are already familiar with the laws of reflection of light. Let's recall them once again. According to the first law of reflection, the angle of incidence is equal to the angle of reflection. The second law of reflection states that the incident ray, the normal on the reflecting surface at the point of incidence, and the reflected ray all lie in the same plane. The laws of reflection affect our daily lives in many ways. In fact, we verify these laws every time we look into a mirror, which is a surface capable of reflecting sufficient undiffused light to form a likeness of an object placed in front of it. The likeness showed by a mirror is called an image. There are two types of images. Real images are the images that can be caught on screen. For example, the images projected on a screen or images taken using a camera are real images. Virtual images are the images that cannot be caught on a screen. Images formed in a plane mirror are virtual, as they disappear when the object is removed. Mirrors can be broadly classified into plane mirrors, which have flat surfaces, and spherical mirrors, which have curved surfaces. Plane mirrors have flat, smooth surfaces. Plane mirrors are most commonly used for personal grooming, decoration, and architecture. These mirrors are constructed silver on one side so that the other side can reflect smoothly. The image of an object formed in a plane mirror is erect, laterally inverted, of the same size as that of the object, and the distance of the image from the mirror is equal to the distance of the object from the mirror. These are standard characteristics of images of objects formed in plane mirrors. Now let us take a look at images formed in spherical mirrors. A spherical mirror is made from a part of a hollow sphere of glass. In other words, it is a plain glass bulging inwards or outwards. Spherical mirrors are further classified as convex and concave mirrors. A convex mirror reflects light from its outer spherical surface and has a silver coating on its inner surface. Convex mirrors are usually used as rear view mirrors in automobiles. A concave mirror reflects light from its inner spherical surface and has a silver coating on its outer surface. Dentists usually use concave mirrors to examine teeth. You need to be familiar with the terminology used in calculations involving spherical mirrors before you get into more detail. Let's start with the center of curvature. Center of curvature, C, is the center of the sphere of which the mirror is a part. Radius of curvature, R, is the radius of the sphere of which the mirror is a part. Pole P is the geometric center of the sphere. In this module, you will learn about reflection in convex and concave mirrors. Objects seen in the mirror are closer than they appear. You may have seen this warning sticker on the rear-view mirrors in your cars and bikes. These rear-view mirrors are actually convex mirrors. Rear-view mirrors help the driver to keep an eye on a large space behind the vehicle by providing a wide field of view. The behavior of the light rays reflected from a convex mirror varies based on the angle of incidence on the mirror. Let's take a look at a few cases of reflection of a light ray from a convex mirror, taking the example of a rear-view mirror. In the first case, an incident ray is parallel to the principal axis. In this situation, the reflected ray appears to pass through the focus. In a rear-view mirror, incident rays parallel to the principal axis enables the driver to see the car traveling behind his car. In the second case, let us consider an incident ray directed towards the center of curvature. Here, the angle of incidence is 0. Hence, the angle of reflection too is 0. Thus, the reflected ray retraced the path of the incident ray and appeared to pass through the center of curvature. This enables the driver to see the parking meter on the other side of the road. Next, look at an incident ray that is directed towards the principal focus. The reflected ray goes parallel to the principal axis. This is how the driver is able to see the traffic signal which the car has crossed. If incident rays strike the pole at an angle with the principal axis, the reflected rays also make the same angle with the principal axis. This helps the drivers of two cars traveling alongside to look at each other in the rear-view mirror of the car ahead. In concave mirrors, such as a dentist's reflector, the reflection of rays is somewhat different from that in convex mirrors. Concave mirrors help enlarge the images of faraway objects or view objects that you cannot directly see due to their position. As in convex mirrors, reflection of rays in concave mirrors also follows certain rules. If the incident ray is parallel to the principal axis, the reflected ray passes through the focus. If the incident ray passes through the center of curvature, the reflected ray retraces the path of the incident ray. If the incident ray passes through the principal focus, the reflected ray goes parallel to the principal axis. If the incident ray strikes the pole at an angle with the principal axis, the reflected ray also makes the same angle with the principal axis on the other side. As a spherical mirror is cut out of a sphere, it has a circular outline. The diameter of this circular outline is called the aperture. All through our modules on spherical mirrors, we consider spherical mirrors whose aperture is small compared to their radius of curvature. For such spherical mirrors, the focal length is equal to half of the radius of curvature. This brings you to the end of this module. In this module, you learned about reflection in spherical mirrors. A ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror, or appear to diverge from the principal focus in case of a convex mirror. A ray passing through the principal focus of a concave mirror, or a ray which is directed towards the principal focus of a convex mirror, after reflection will emerge parallel to the principal axis. A ray passing through the center of curvature of a concave mirror, or directed in the direction of the center of curvature of a convex mirror, after reflection is reflected back along the same path. A ray incident obliquely to the principal axis towards the pole of the mirror on the concave mirror or a convex mirror is reflected obliquely. The incident and reflected rays follow the laws of reflection at the point of incidence, making equal angles with the principal axis.